We're going to shift gears here now. We've been talking for the last few days about things involving electrons. The discovery of the electron by Thomson, 1897, and then the discovery of the charge and the mass of the electron by Millikan a few years later. Now we're going to go a little bit deeper, literally a little bit deeper. We've got the electrons that we now know circle around the nucleus. Now we're going to look at the nucleus itself, what takes place in the nucleus, different processes that can exist within the nucleus. But before we do that, we have to look at some notation so that we can understand what we're looking at for the next few days. It's called isotope notation. If you've taken chemistry class, you're probably familiar with this already. I always get mixed up which one's A and which one's Z. We're not going to lose any sleep over which letter is which. What we want to focus on is which number goes where. X represents the chemical symbol. So if it was carbon, then X would be C. If it was lithium, then X would be Li. If it was calcium, it would be Ca. If it was uranium, it would be U. If it was thorium, it would be Th, and so on. You're going to get that off your periodic table. Z, the bottom number, is called the atomic number. The atomic number is the number of protons. Now, the number of protons can vary between different elements, but for one particular element, it will never change. Carbon always has 6 protons. Uranium always has 92 protons. Lithium always has 3, I believe, protons. Hydrogen always has 1. Thorium always has 90 protons. It doesn't matter what version or isotope of an element you have, it always has the same number of protons. If you change uranium from 92 protons to something else, then it's not going to be uranium anymore. A, this is what we call the mass number. It's the number of protons plus the number of neutrons. This number can change, but yet keep the element the same. So for instance, carbon, which I said always has 6 protons, sometimes has 6 neutrons, giving me a mass number of 12. Sometimes carbon has 7 neutrons, giving me a mass number of 13. Sometimes carbon has 8 neutrons, which gives me a mass number of 14. Different mass number, always the same atomic number, always the same number of protons. These 3 versions of carbon are what we call isotopes. Different versions of carbon, different isotopes. Same number of protons, different number of neutrons. That's why we call this isotope notation, because it describes for us the differences between all these different isotopes. Yep.
So why is it different than the standard periodic table mass at the bottom?
Well, it would actually depend upon the periodic table that you have. Yeah. Every periodic table is just formatted a little bit differently. Sometimes the mass number will be on the bottom, sometimes the atomic number on the bottom. I think on the one you have here, oh, it is, yeah. Yeah. Sorry, the atomic number is on the top there in your periodic table here. Okay, but don't lose any sleep over that. You need, if you want to find the atomic number on your periodic table, the atomic number, take the smaller one. If you want to find the mass number, don't go to the periodic table. Because mass numbers are different for each different isotope, right? You've only got 1 carbon listed on your periodic table. But how many different isotopes of carbon exist? You can't get the mass number from the periodic table. You can get the atomic number, but not the mass number. Let's take a look at a simple example here. Gold, 197. How many neutrons are contained in a gold 197 nucleus? Well, how many protons, first of all? 79. 79 protons. Even though we weren't asked that question, we know we have 79 protons. How many neutrons do we have? 197 minus 79 gives me 118 neutrons, right? 118 plus 79 gives me 179. This is true isotope notation. We could see it written slightly different as well, though. Maybe we see it written like this. Does that mean the same thing? Sure it does. We don't have the atomic number. Where do we find it? Periodic table. Okay, we have to have the mass number, but we don't have to have the atomic number because we can get that on the periodic table if we have to. Sometimes you might see it written like this. Means the same thing. Like gold 197 is that version of gold. 197 protons and neutrons. How many protons? 79. Check your periodic table. I'll give you just a minute to see if you can answer these questions up to 791. Okay, let's take a quick look at number one. How many neutrons in magnesium 24? 24 minus 12 is 12. Good. The mass number for uranium atom that contains 92 protons and 146 neutrons. Mass number is 92 plus 146, which we can see there gives me 238. Good? Easy enough, right? Listen, we're not doing this isotope notation because that's something that we have to know as an end per se. Okay, that's not the end itself. Okay, that's a tool that we're going to use in the rest of the unit as we're studying the nucleus. If we're going to identify a nucleus, we have to have a way of identifying it, a way of describing it. That's going to be with isotope notation. Now we're going to talk about radioactivity, which you're going to see in a little while, requires us to know this isotope notation. Radioactivity is a natural process. That means it happens on its own. It's a random process, which means it happens when it wants to happen. So in other words, we don't control whether it happens or not, and if it does happen, we don't control when it happens. What is it exactly? Well, it's a process whereby one nucleus decays into another nucleus. So unlike in chemistry class, when you learn that carbon always is carbon, and lithium always stays as lithium, well, carbon can actually change into something else now. And lithium can change into something else, and uranium can change into something else. A nucleus splits up. It changes into something else. It's like alchemy, right? Like making one element from another. The resulting radiation is ionizing. What does that mean? What's an ion? What's an ion? You guys know this. An ion is you guys took Chem AP, right? What's an ion? Go ahead. It's like a charged atom, right? It's like a charged atom. It's an atom that has extra electrons or extra protons, right? Deficiency of electrons. So it's charged, either positive or negative. Ionizing radiation is radiation that has the ability to ionize atoms, to turn atoms into ions. So what's the big deal? Well, sometimes there isn't a big deal, but sometimes there is. We've got a whole bunch of atoms floating around inside our body, right? We've got ions floating around inside our body. But if we get extra ions floating around inside our body that aren't supposed to be there, maybe they were caused by some kind of exposure to a radioactive decay, to ionizing radiation. If we get extra ions floating around that aren't supposed to be there, then we get chemical reactions starting to take place that aren't supposed to take place inside our body. Well, that's bad news. Our whole bodies are based on chemical reactions, but pretty predictable chemical reactions. If we have unpredictable chemical reactions taking place, then funny things start happening to us. Like we get sick, we get radiation poisoning, we might even develop cancer. We might have genetic mutations. Okay, we might turn into the Incredible Hulk. Maybe not. We might get cataracts in our eyes. When you go get an X-ray, X-rays are ionizing radiation as well, by the way, although it's not coming from radioactivity. It still has a similar effect. When you go get an X-ray, normally they'll cover you with this lead vest, right? They want to protect other parts of your body from exposure to ionizing radiation. Ionizing radiation does damage to your body. If you're trying to X-ray a shoulder, it will do damage to your shoulder. Not irreparable damage. Generally, your body repairs itself quicker than the damage can be done, so it's not a big deal. Unless you're getting 100 X-rays, then it tends to be a problem. But they don't want to expose other parts of your body unnecessarily to these X-rays. Does that make sense? Because they're ionizing radiation, because it causes atoms to turn into ions, and that's not good, because it can lead to all kinds of these things like, vomiting and general sickness and cancer and cataracts in the eyes and genetic mutations and yeah, all kinds of crazy things. We're going to talk about 3 kinds of radioactivity: alpha decay, beta decay, and gamma decay. An alpha particle has the symbol or the notation 4,2 alpha. That means an alpha particle actually consists of 2 protons and 2 neutrons. An alpha particle is a piece of an atom, a piece of a nucleus that's broken off of that nucleus because the nucleus wasn't stable. It's kind of like you got a big ship in the North Atlantic. You got that iceberg over there looking at the North Atlantic, or looking at the ship looking at the iceberg. The iceberg isn't quite stable. It kind of wants to break apart. Sometimes it'll happen completely on its own. Sometimes it needs to be bumped a little bit by the ship. And then a chunk of the iceberg breaks off. This is the chunk of the iceberg that broke off. Now, there's still an iceberg that remains, but the iceberg that remains is a little bit different than the one that we started with, right? Because it's missing a big chunk of ice now. It's missing the alpha particle. The alpha particle has left the nucleus. So now we got something else. If it was uranium-235, now it isn't anymore because there's a chunk that's broken off. Talk about why it breaks off in a minute. Beta decay we break down into 2 subcategories: beta minus and beta plus. How many protons again in an alpha particle? 2. How many neutrons in an alpha particle? 2. Good. How many protons in a beta minus particle? -1. What? That doesn't make any sense. How can you have -1 protons? What's a -1 proton? It's an electron. It's an electron. In fact, sometimes, because 2 protons, 2 neutrons is exactly the same thing as a helium nucleus, sometimes we call an alpha particle a helium nucleus. A beta particle is exactly the same thing as an electron. Why does an electron get kicked out of a nucleus when there are no electrons in the nucleus to begin with? We'll deal with that one in a minute. What about this one? Beta positive decay. How many protons? No. How many protons and neutrons combined? 0. Well, then how many protons? 0. What's the +1? It isn't a proton. It's what we call a positron. It's the antiparticle of an electron. It's antimatter. How many people have read Angels and Demons or watched the movie Angels and Demons? Okay, they talk about antimatter. When matter and antimatter collide, they annihilate each other and produce pure energy. This is what we're talking about, antimatter. A positron is the antiparticle of an electron. Well, how do you get a positron out of a nucleus when the nucleus doesn't have any positrons in it? And we'll see in a minute. Kind of like magic, almost, yeah, almost. Gamma decay. 0, gamma. How many protons? 0. How many neutrons? 0. How many electrons? 0. How many positrons? So what is this? It's just electromagnetic radiation. Remember, on the first day of our electromagnetic radiation unit, we went through the spectrum and we identified how each of these types of EMR were produced. X-rays, rapid deceleration of electrons, right? Microwaves, oscillation of electric charge. What do we say for gamma rays? Nuclear decay, radioactive decay. Okay, now we're going to learn a little bit more about it. Now let's take a closer look at each of these types of particles that are produced as a result of nuclear decay, as a result of unstable nuclei, and figure out exactly how each of them are produced. Alpha decay occurs when you have large nuclei, big nuclei. And that big nucleus is unstable because you've got too many protons. Now, too many protons in itself doesn't lead to an unstable nucleus, but too many protons relative to the number of neutrons does. Here's why. The nucleus has three forces acting in it. We're going to look at two of them right now. There is the electrostatic force. The electrostatic force is a repulsive force. It can also be attractive, but in the nucleus it's repulsive. That acts between proton and proton. In other words, protons push each other away from each other. They want to break up the nucleus because they're pushing each other away. We got 21 people in this class. If 21 of you get together in the middle of the room and you start pushing each other away from each other, then you will break the group up. The group won't be together anymore because of this repulsive force, right? It's an and. Proton, that acts between protons and protons. But there is also in the nucleus what we call a strong nuclear force. And that strong nuclear force is an attractive force. And it acts between protons and neutrons. So it acts between everything. If the attractive force, the strong nuclear force, is bigger than the repulsive force, then the nucleus is stable. It likes to stay together. But if the repulsive force is bigger, then what happens? It breaks apart. If you have too many protons relative to the number of neutrons, then you get too big of a repulsive force relative to the attractive force. The nucleus is unstable, and this chunk breaks off. This little piece of the iceberg right here breaks off. The alpha particle leaves the nucleus. Now you're left with still a nucleus, a pretty big nucleus, but a little bit smaller than you had before. It's slightly more stable than it was before. Maybe it's completely stable, but it's at the very least closer to being stable. So you got a big nucleus, you got too many protons relative to the number of neutrons, breaks apart in an attempt to become more stable, in an attempt to improve the ratio of protons and neutrons. Well, beta decay occurs in any size nucleus, big or small. Beta minus occurs when you have too many neutrons. Now, wait a sec, that should be good, right? Because that creates a stronger attractive force. Neutrons contribute to the attractive strong nuclear force, but not the repulsive force. So that should be a good thing. The problem is that this nucleus is in an energetically unfavorable state. So there's this fine line that the nucleus has to balance here. You get too many protons, the repulsive force is too big. You get too many neutrons, the energy state isn't favorable. It's got to be this nice balance of protons and neutrons to make it stable. Well, what's the solution to this, to have too many neutrons? This is the crazy part right here. What happens is a neutron actually changes into something. It transforms into a proton and an electron. I like to think of it as a club. Call it the nucleus club. Give me the two members of the nucleus club. Protons and neutrons. All right. So one day, all the protons and neutrons get together in the nucleus club. They get together and say, you know what? Been thinking lately. I think we have too many neutrons in this club. Well, they don't want to just kick one out because they like neutrons. They don't want to just get rid of one. They like them. So what do? They get together and they come up with this brilliant idea. You know what? Let's not kick them out. Let's just change them. Let's change them into a proton. So they try that. They change them into a proton. But by the law of conservation of charge, they also have to make an electron in the process, right, to balance that out. And they look at it and say, you're the proton. We like you. You're the electron. Get out. Electrons aren't welcome here. This is the nucleus club. Protons and neutrons are welcome in the nucleus club, not electrons. So the electrons have to leave. The electron that leaves is the beta particle. That's the particle that leaves, right? That's the particle that leaves the nucleus. So now Now you've changed the nucleus into something else again, not because you've taken away protons, but because you now have an extra proton. Carbon has become nitrogen. Atomic number 6 has become atomic number 7 now. Yeah?
Does the electron actually complete the atom or does
Either one. Depends on its energy. Beta plus occurs once again when you have too many protons. But something different happens here. It's a different process than alpha decay. Too many protons, the nucleus club says, hey, we got too many protons, but we like protons. We don't want to just get rid of the proton. Let's change them. Let's change the proton into a neutron. Hey, look at that. We changed a proton into a neutron. We like them both. But now this improves the ratio. But we got to make something else in the process so that the law of conservation of charge isn't violated. What else do we make? Positive becomes neutral and positive. Positron. The nucleus club, they get together and say, hey, we're happy with this. We got one less proton, which is what we wanted. We got an extra neutron. That's good. But we got a positron? We don't want him. Get out. So now we're left with one less proton and an extra neutron. And then the positron gets kicked out. That's the beta plus particle. Now the gamma ray, oh, this one's the easy one, kind of. This one's kind of just a byproduct of the above. When something like beta decay occurs, the nucleus is left in an energized state, in an excited state, but it doesn't want to be there. Something's happened to leave the nucleus in an excited state, but it doesn't want to be there, so it goes back down to its normal state. But when it does that, it has to give off energy. The energy that it gives off is a photon. It's a gamma ray. You can imagine you're in this club, and you've just watched a neutron transform into a proton and an electron. You'd be excited too. Now this excited nucleus, because something's just changed from a proton or neutron into a proton and electron, it's excited. It's kind of level-headed, right? It doesn't want to stay excited, so it just goes back down to where it was. But as it does that, the gamma ray gets fired out. The energy gets dissipated as gamma. Yep.
So would the difference in mass between a neutron and a proton mass?
No, not exactly, because there's an energy mass equivalence analysis in there as well. It's a good thought. Doesn't quite work though. Okay, I want to take a look at two more quick properties of alpha, beta, and gamma decay. Alpha particles have a charge of 2 plus, by the way, because they have 2 protons. Beta particles have a charge of -1 or +1, depending upon whether it's an electron or a positron. And then gamma rays are neutral. I want to look at the penetrating power. In other words, the ability that these things have to penetrate matter, to go through matter, to go through things. And then finally, the ionizing power. We know they're all ionizing radiation. How much ability do they have to ionize matter? Here's the good news of alpha particles. They have a very, very low penetrating power. Very low. Maybe a sheet of paper. If you ever get mad at me, and you want to come in and you want to teach me a lesson, don't use an alpha particle gun. Because I'm going to take this piece of paper that Jake, this little booklet that Jake has right here, I'm just going to hold it up in front of me and use it as a shield. And it's going to shield me just fine from your alpha particle gun, because the penetrating power of alpha particles is maybe a piece of paper. I'll have a big piece of paper. The penetrating power is very, very low. Gamma rays, the penetrating power is very high. Gamma rays can penetrate several centimeters of lead. And the lead's pretty dense. And if you want to shield, say, you've got a cancer treatment center, which they use gamma rays to treat cancer because it has a really high penetrating power. Okay? The room needs to be shielded by lead and concrete so that somebody standing outside the room isn't exposed to gamma rays. Beta particles, it's in between. It could penetrate a couple centimeters of flesh. Oops, can't spell flesh. But it could penetrate your skin, but it's not going to get to vital organs inside your body. That is, unless you consume something that produces beta particles after it's already inside you. And then it's not going to have a tough time getting in. It has a tough time getting out. What about the ionizing potential? Well, here's kind of the flip side of it. Although alpha particles have a very low penetrating power, they have a very high ionizing power. Gamma rays have a very high penetrating power. I don't want to say they have a low ionizing power, but they have the lowest of the three. Beta particles, they're in the middle. They're the fence sitters, right? They're in the middle for penetrating power. They're in the middle for ionizing power as well. So which do you want to be exposed to? If you got to be exposed to something, which do you want to be exposed to? Depends on context, right? It completely depends upon context. Okay? There's a trade-off of penetrating power versus ionizing power. Okay? You look at this and say, beta particles are probably the best thing to be exposed to, but it does really depend upon context. Got it? We're going to wrap it up there for today. Perfect timing. We'll pick it up there tomorrow, okay? Have a good night, everyone.